Hello, everybody. In today's lesson, we're going to talk about 3.3 solids, liquids, and gases. We're going to do a part one, part two on this. We're going to talk about properties of solids, liquids, gases, and kinetic energy. So, solids, let's talk about quickly what a solid really represents. So, in a solid, it's a state of matter. The particles are not really moving around. Well, they are moving, but they're moving very, very slowly. So, the motion of these particles is extremely limited. And what happens is that they're really close together. So if you think about any sort of solid as a state of matter, it's because they're not really moving that much. The structures are actually held by intermolecular forces and or chemical bonds, meaning they could be covalent or they could also be ionic. And that structure is influenced by the ability for them to get packed in together. So if they are packed in together really nicely, they're going to be a very strong solid. And if they're not, they're going to be a very weak solid. And that really depends on their arrangement in that area. Let's talk about the first type of solids called an amorphous solid. And these are usually really randomly arranged. The particles have no structure, unlike something like a crystal lattice structure. And the structures really lack defined faces and shapes. These molecules generally are not going to stack well with each other. An example of this, an amorphous solid, is glass and rubber as an example. So if you think of solids, you have usually rubber. You can kind of move them around a little bit. Glass, it's kind of like it has this ability to not really create structure, so that's why it kind of breaks really easily when you hit on it, versus something like salt. Crystalline structures are a little different. These are the ones that are arranged in a more of a definite pattern. They follow a dimension in 3 dimensions, and they actually have what they call these unit cells. So they constantly repeat after each other. And these macroscopic structures generally have definite angles. And the example of this is quartz and ionic solids. They're crystalline structures. So generally what you find in crystalline structures is very rigid structures that have a very, very good pattern. And sodium chloride is a great example of that. It's a crystal structure. Now, amorphous and crystalline structures generally are going to look like this. So if you take a look at glass as an amorphous structure, it doesn't really have this definite shape as I was explaining earlier. Same thing with rubber. It's a solid, but it technically doesn't have that motion. While quartz is a crystalline structure, it has a very nice structure here, and all of them are tightly packed with each other. And the example here is the arrangement of oxygen and silicon. Silicon and oxygen are kind of put together in this nice structure, and they're placed in alternating areas. So let's talk about liquids. Liquids have this situation where they are constantly moving around. We already know a liquid is obviously like water, constantly moving, and they undergo a translation to respect to each other, meaning that they're able to move around, and that strength is really going to be caused by these intermolecular forces that are going to be present in the particle. These intermolecular forces, such as hydrogen bonds, London dispersion forces, ion-ion, ion dipole moments, are going to really affect the strength of that water molecule. In liquids, the particles are close to each other, and they behave in between a liquid and a solid and a gas. Now, talking about the volume of solids and liquid phases, so solids and liquid phases are generally going to have very similar molar volume. So if you take a look at a liquid and a solid and you put them in a container, generally, they're going to have the same kind of shape. The density is also very similar in both cases, not identical, but similar because of the fact that they're, like I said, it's going to be closer more to a solid than to a gas. And so ice has a slightly larger volume than water. So that's the only exception to that rule. If you take a look at ice, ice is less dense than water, and that's why it floats. And so if you take a look at solids are going to have a slightly smaller molar volume than their liquids. And so if you take a look at volume expansion, liquids are going to have obviously a little bit more because of the fact that the molecules can move a little bit more. So let's take a look at an example here with the solid and the liquid phase. So in the solid phase, you can see that the molecules are tightly arranged, and they're, the charges are really nicely put. In a liquid phase, they're a little bit more of a random motion. So they're not really moving around. They're all over the place. And so what you're really seeing right there is a situation where the solid phase and the liquid phase are behaving differently depending on the charges that you're putting in. So let's talk about gases. Now, gases are a little bit different in the sense that they have pressure. So unlike solids And liquids, we do have like water pressure, we do have some of that going on, but it's not as big as a gas. And so a gas actually has this idea called pressure, which means you're going to put an amount of force per a certain area, and that pressure is going to really be calculated by dividing the force in the area. And so what happens is gases tend to bounce around surfaces. They like to put them in a box, put them in a balloon, and they're going to be bouncing around all the time. And so what happens there is that they're going to be smashing every single area per unit of time. And each time it collides, it creates some force. And that pressure is going to be very, very constant at all temperatures. Now, here's an example of how that looks like. Here's a person and we got ATM pressures hitting us all around. And in this case, we have gas pressures hitting that person at 1 ATM all around our bodies. And generally, we don't really feel it because it's in equal directions. But if we were to push on one side or increase the pressure on one side, you could definitely feel that change. So here's an example of something where you'll find sucking gas out of a can, okay? Now in this case, what you're starting to see is that when we talk about sucking particles out of a can, what you're really doing is you're creating what they call a vacuum. So here's a box, and then inside you have equal pressure, so the can doesn't really break. But the moment you turn the vacuum pump on, you pump out all the gas particles, and all of a sudden the outside pressure collapses the can. And so in this case, the pressure on the outside is greater than what the pressure is on the inside. And so what you're really seeing there is this difference in pressure, and that's the reason why the can crushes. So a very classic example of this is when you're heating up gas particles and then you cool them down real fast. Well, when you do that, you actually crush that can because of the outside pressure. So let's talk about barometers. So as a recap, gases generally are going to be measured in several ways, the pressure, in torr, in millimeters of mercury, and atomic ATM, or atmospheric pressure. And so in this case, the atmospheric pressure is all the pressure around us. And generally, if you do this experiment, you could see that a barometer measures how much pressure there is on the outside. What we do is we chop open a little piece of glass here, this tube, and what happens is that you allow the air to come in and press on the mercury. The mercury is at the bottom. As the mercury gets pressed, it actually pushes itself up. And what that does is that you can actually measure how high the mercury went up. So depending on how high the mercury went up, you can actually measure that pressure. So in this case, it went up by 760 millimeters. That's the distance that the mercury went up. In that case, you can tell that that pressure is 760 millimeters of mercury. So this is another way to kind of measure atmospheric pressure, is by looking at how high that mercury went up. Now, let's talk about the gases real quick. So in the gases phase, there's going to be several laws that you have to know. The first one's called Boyle's law. And Boyle's law basically studies that relationship between gases and volume. And so in this case, what you'll find is Boyle's law is considered to be basically this idea where you're going to multiply volume times pressure. And so what you're going to find here is if you multiply volume times pressure, you're going to find that they're both inversely proportional to each other. So V1 times P1 equals V2 times P2. So in other words, if I increase volume, I should decrease pressure. If I decrease volume, I will increase pressure. And that's basically going to be that relationship that you'll find. Now, here's a great example of that. So if you take a look at this picture here, as you're increasing pressure, you're going to half the volume. And you could also do it the other way, where if I change the volume, I can also change the pressure. So depending on how you look at it, you can kind of look at that relationship. Now, temperature is a little different. Temperature works in the average kinetic energy of atoms. So as molecules are moving around, you take a little snapshot of how fast these molecules are moving. And so we're going to use the term Kelvin. Kelvin basically means that that's going to be the definition of how much kinetic energy you have. And so as kinetic energy doubles, the Kelvin temperature doubles. So that's going to be proportional to the temperature that we have. Obviously, kinetic energy is the movement of these molecules, and these gas particles are moving really, really fast. So the Kelvin temperature really is a measurement of that average kinetic energy. All right, so that brings us to kinetic energy of gas molecules. So we have three types of gas molecule energies. I need you to make sure you know these. The first one is called translational energy. Second one's called rotational energy. And the third one's called vibrational energy. And so most of the gas particles' kinetic energy is related to translational, meaning that they are moving in straight lines. And you'll find later on that there's molecules that move in different speeds later, depending on whether they're in a gas or they're getting heated up. So Charles' law really refers to the second law of gases, which refers to the relationship between temperature and volume. So in this case, we have V1 and T1. And in this case, volume is proportional to temperature. So in this case, what you're going to find is that you must use Kelvin. So in other words, if temperature goes up, volume should go up. If temperature goes down, volume goes down.